Welcome to the Laplace transform of derivatives. So if we're going to be working with differential equations, it's extremely useful to know how to take the Laplace transform of the derivative of a function. So the theorem that we're going to work with is if f is continuous on the interval from 0 inclusive to infinity, and of exponential order s naught, and if f prime is piecewise continuous on 0 to infinity, then the following statements are true. First up, the Laplace transform of f prime of t exists for s greater than s naught. And next, that Laplace transform of f prime of t is simply equal to s times the Laplace transform of f of t minus f of 0. So we're going to go ahead and work through the sort of a sketch of the proof for the case that f prime is also continuous. I'm not going to do the complete proof for the case f prime is piecewise continuous. So let's do a proof sketch. For the case where f prime is continuous as opposed to piecewise continuous. So in that case, what we have is the Laplace transform of f prime of t is the improper integral from 0 to infinity of e to the negative st times f prime of t dt. This is equal to the limit as capital T goes to infinity of the definite integral from 0 to capital T of e to the negative st times f prime of t dt. And if we run integration by parts on this, if we take u to be e to the negative st and dv to be f prime of t dt, differentiating that e to the negative st, sorry about that, we would have negative s e to the negative st. Integrating f prime, we get f of t. So you're adding the product of e to the negative st times f of t, subtracting the integral of negative s e to the negative st times f of t. So we wind up working with, we have the limit as capital T goes to infinity of, we will do e to the negative st times f of t, and then evaluate at 0 and capital T and subtract. And then we are subtracting the integral from 0 to capital T of negative s e to the negative st times f of t dt. This first part, we are looking at the limit as capital T goes to infinity of e to the negative s times capital T times f of capital T minus f of 0 We are subtracting a negative s times that definite integral. So this becomes plus s times the definite integral. I'm going to actually, so plus s times the definite integral from 0 to t, e to the negative st, f of t dt. If we split our limit, we have a limit as capital T goes to infinity of e to the negative s times capital T times f of capital T minus f of 0 plus s times the limit as capital T goes to infinity of the definite integral from 0 to capital T, e to the negative st, f of t dt. This second limit here is just the improper integral from 0 to infinity. So this is just the improper integral from 0 to infinity, e to the negative st, f of t dt. There's a multiplying by s out front. The limit as t goes to infinity of e to the negative st times f of t, that just goes to 0, since f of t is of order, exponential order. As long as s is greater than s naught. So again, for t large enough, f is bounded by e to the s naught t, or m times e to the s naught t. And if s is greater than s naught, then we'll be looking at a negative exponent and it'll go to 0. So essentially what we have then is that the Laplace transform of f prime of t is equal to 0 minus f of 0 plus s times the improper integral from 0 to infinity of e to the negative st times f of t dt. This improper integral is precisely the Laplace transform of f. And so we get that this is s times the Laplace transform of f of t minus f of 0. So this is, again, a sketch of the proof in the case where f prime is also continuous. When f prime is piecewise continuous, you wind up having to break your integral up into a bunch of smaller integrals, since the fundamental theorem of calculus requires continuity. But we will only worry about this one particular case for the proof. What we get from here is we can extend this. So note, we can extend the theorem right. If f prime is also continuous, and of exponential order s naught, then we have that the Laplace transform of the second derivative of f should be equal to s times the Laplace transform of f prime of t minus f prime of 0. And then we know the Laplace transform of f prime. So we are looking at s times, in replacing that Laplace transform of f prime with s times the Laplace transform of f of t minus f of 0. And then all of that minus f prime of 0. And so we get that the Laplace transform of the second derivative of f is equal to s squared times the Laplace transform of f of t minus s times f of 0 minus f prime of 0. And furthermore, in general, if f and all its derivatives through the n minus first derivative. Actually, let's just go through the nth derivative are continuous. So if f and all its derivatives through the nth derivative are continuous and of exponential order s naught, then we get that the Laplace transform of the nth derivative of f is equal to s to the n times the Laplace transform of the n minus, times the Laplace transform of f of t minus s to the n minus 1 times f of 0 minus s to the n minus 2 times f prime of 0 minus all the way down to minus the n minus first derivative of f evaluated at 0. So this trick is useful. We can find all the Laplace transform of all derivatives of f in terms of the Laplace transform of f and its initial conditions. So why is this useful? Essentially, what we can do is we can take an IVP and we can convert it into an algebra equation by taking the Laplace transform. So we can take an IVP by take an IVP and convert it into an algebra problem. By taking the Laplace transform of the differential equation. So in the next videos, we will practice taking the Laplace transform of a differential equation, working with the algebra, and then essentially using the inverse Laplace transform to take us back to the final solution.